So good afternoon, my dear students. So today we have another theorem. So far we have done central limit theorems for IIT random variables. So today's theorem by Liapounov is on a sequence of random variable xn, which are independent random variables. Sequence of independent random variables only. So not necessarily IID. So you note this point as sequence of independent random variables. It's only independent, not necessarily IID. And the condition is that for a delta lying between 0 and 1, delta is a fraction. We define mu n delta is expectation xn minus expectation xn to the power 2 plus delta for all n. Then the sequence obeys the central limit law if limit summation k goes from 1 to n, limit over n, mu k delta by variance of Sn to the power 2 plus delta by 2 is equal to 0. So this whole thing is the Lyapunov condition. This is Lyapunov condition. Okay. First note that the proof is of the theorem is beyond our scope. So we will discuss corollaries on these theorems. So first note that this theorem gives the sufficient condition for a sequence of independent random variables to obey the central limit law. Corollary 1. Consider a sequence of independent random variables xn which are almost surely uniformly bounded. Then variance Sn tends to infinity under Lyapunov condition. Okay. So suppose the Lyapunov condition holds in the proof. So Lyapunov conditions we have already seen. This is the Lyapunov conditions. This is the Lyapunov condition. This holds, and we define mu k like this. Now since xn is almost surely uniformly bounded, we have for some positive a probability absolute xn less than a is equal to 1 for all n. The meaning of uniformly bounded means this. First, uniformity is for all n, and almost sure means probability absolute xn less than a is equal to 1. So combining together we call it almost surely uniformly bounded. So under that condition we have this equation number 2. Now without loss of generality we assume that expectation xn is equal to 0 for all n, so that mu k delta is equal is definition of mu k delta is changed. Expectation xk will be 0, so expectation of absolute xk to the power 2 plus delta. So you make it 2 absolute xk 2 delta, it is separated, 2 plus delta is separated here. This is less than or equal to a to the power delta expectation xk to the power 2. So for this part expectation xk, you know, because of equation number 2, that is probability absolute xk less than delta is equal to 1. That means their expectation will be less than a. Okay. So therefore expectation xk to the power delta will be less than a to the power delta. So that is why this inequality is coming up. So expectation xk square is variance of xk, because expectation xk is 0, so this square will be variance of xk simply. This is equation number 3. Now we have to prove that variance Sn tends to infinity. To contradict, variance Sn tends to some constant which is a finite. Then limit of summation summation k goes from 1 to n mu k delta c to the power, that Lyapunov condition equation number 2 becomes this one. So mu k delta is finite here by equation number 3, and c is finite, and so c to the power 2 plus delta by 2 will be finite. So finite by finite, so this is not equal to 0, which contradicts our supposition, and therefore variance Sn will tend to infinity under the Lyapunov condition. So this is the first corollary. As a corollary number 2, here also consider the sequence of independent random variables xn which are almost surely uniformly bounded, and the Lindbergh condition holds if and only if variance Sn tends to infinity. So only if part is corollary 1, one part we have already proved in corollary 1. So the other part, that is the if part, suppose variance Sn tends to infinity, we have to show that Lindbergh condition holds. So because of almost sure uniformly bounded, here again this is the meaning of almost sure uniformly bounded. So this means moments of all order exist for xn. So this, because of this, moments of all order exist for xn, that is expectation x to the power r exists for any r positive integer. So without loss of generality, here also we have expectation xn is equal to 0 for all n. Now definition of mutual delta is as it is in corollary 1, here a to the power delta variance xk. Now this implies the summation of mu k delta less than or equal to, take the summation. Now here also we take the summation a to the power delta variance of summation xk. This is nothing but variance of Sn. Summation xk is variance of Sn. So this divided by variance of Sn to the power 2 plus delta by 2 is less than or equal to a to the power delta by variance Sn delta by 2. Actually this one and this one you simplify. This is, you put it in the numerator, this is in the denominator, then variance Sn will remain. This is 1 plus delta by 2, so 1 will remain. Is easy. Evidently, if variance Sn tends to infinity, Sn tends to infinity, it follows from 3 that this part will be in the limit 0. So limit of this quantity Sn tends to infinity will be 0. So this completes the proof. So for today we will conclude here. Stay safe, stay home. Any difficulty you can put up in the WhatsApp. Have a good day.